guys, welcome back, and today the video is about entropy. So let's talk about entropy and what entropy really is. Let my ex-student to answer you.
Okay, so entropy is basically the measure of randomness in a system.
Okay, that's good. Okay, so after the video, we're gonna finish entropy. We're gonna learn how to calculate Gibbs Free Energy. Then we're gonna do what else? Yeah, these two are the most fundamental stuff that we'll be covering in the video. And please go through the recording. Yeah, that's all. Alright, guys, the definition. We call it as the degree of randomness. Sure. Guys, come on.
Teacher, you didn't send me.
I asked someone to listen to you again. So we call it as degree of randomness. Okay, of a system at a specific temperature. Yeah. It refers to dispersal, blah blah. Okay. So guys, how does this
Just drink some coffee.
system becomes energetically more stable, right? When they are more random. Okay.
Why the notes like so?
Yeah, randomness. So guys, the more the randomness, the higher the greater, not the higher. The greater the randomness, what happened to the entropy? The greater the entropy. Highlight this. The greater the randomness, the greater the entropy. Yeah.
Is that burger?
The system, right, refers to the chemical reaction itself.
Oh my lord, who's that?
Who's that?
So badly.
He has a wife. Why are you asking, right? Oh, yeah, sorry.
No respect for the wife.
Yeah.
Who they get?
So after you get wife, you don't care already. How she here? Wait, actually, what happened to the dog? Was it just for the wedding?
I think so. No.
Then?
Now I'm too lazy to cook. Maybe it will come back.
Oh, so you're
The
like,
clean diet will come back soon.
so you're like, wait, are
Yeah,
you still working on?
No. Okay, so guys, the total entropy. Okay, so total entropy, right, made up of entropy of the system. Okay, and also, what is entropy of the system, right? Remember, yeah, entropy of the system, right, is the reaction itself. So we are referring to the reaction itself. And also we have entropy of the surrounding. Alright, guys, as for entropy of surrounding, right? Okay, this is at what temperature? Yeah, happens at which temperature?
Oh. I don't think it's it.
Okay, guys, example, magnesium react with sulfuric acid. The system, right, refers to the reaction itself. Okay, however, some energy is released into the surrounding. Yeah. Let's compare entropy value. Alright, guys, to compare entropy value, right? Okay, pressure must be at 10 to the power 5, which is room, and room temperature also. At the same time, all the substance, right, must be under normal physical state. Yeah. For example, solid must be a gas, it must be a solid. Sodium must be a solid, chlorine must be a gas, things like that. Okay. Okay, so guys, under this condition, the unit of standard molar entropy, right, is joule per mole per Kelvin. Okay, and guys, standard molar entropy value, right, is always positive. Yeah. Done.
The answer came from the Too bad. Yeah, exercise. Then the next thing in demand, Melvin, what happened?
Alright, guys, next page. Page 2. Let's go.
It's a drama, lah. It's a good girl. Shut up. Oh. He's affecting all your friends, bro. Especially Johnny, bro.
Alright, guys, now let's look at entropy of different physical states, solid, liquid, and gas. Alright, guys, if you look at solid, right, solid is always arranged in the crystalline. So this is having the least randomness, right? So this is definitely the least random. So guys, when it is least random, right, which means it's the having the least entropy, right? Okay, and as for gas, this is the most random, right? Oi. Which means it's having the highest entropy. Yeah?
What about it?
Done.
Oh, yeah. He's so insecure.
Alright, guys, next. When a solid change into a gas, when a solid change into a liquid, how? Okay, so regularly arranged lattice of particles, like close together, start to vibrate, right? Then it changes into irregular arrangement, therefore entropy increases. Why? Because the randomness increases. Highlight the word entropy increases, randomness increases. Will never give me a spoon. How am I gonna finish? Alright, guys. Next, what about liquid to gas? Alright, guys, from liquid to gas, the same thing, right? Okay, so randomness increases, correct? So when randomness increases, I can say that entropy increases as well. So it gets more random, hence entropy value increases also. Entropy. Yep, entropy. Do this question, go, go, go. Alright, guys, next. The number of particles. Again, when there is an increase in the number of particles, right? Okay, highlight it. Okay, I want you guys to write it down. When there's more particles, okay, it's gonna be more random. This one up, what? No? Solid turn into gas, can see that? So basically there is an increase in entropy, right? Can see that? So guys, I can say that there is definitely an increase in entropy because the reactant is a solid, okay, which has the lowest entropy, right? Okay, a gas is produced and it has the highest entropy. Hence, the change in the entropy of the system is positive. Let's look at the number of molecules. So 1 plus 3, basically you have 4 molecules and turn into 2 molecules, right? So guys, is there a decrease or increase in entropy? Yes, there is a decrease in the entropy. Why? Okay, because it's less molecule, right? Okay, so because that is, okay, because this is because the molecules, number of molecules, right? I think number of gaseous, okay, good. Number of gaseous molecule, okay, has decreased, right? There are 4 moles in the reactant, but only 2 moles in the product, right? So guys, what happens to the system then? Is it positive or negative? Well done, negative. Good job. Next, we will be doing a bit of electrochem, yeah. Okay, yeah. I let you guys go 7 minutes earlier. I have the same hoodie. Eh, bestie. Yeah, sorry. I'm a very emo kid today. You see. Look at page 4. Alright, kid, we have exothermic versus endothermic reaction. Okay, guys, for exothermic reaction, now always remember energy is released or absorbed. Energy is released to the surrounding, right? Okay, so right now you have more ways of arranging the energy and entropy increases. Guys, this is not important. I'm just going to rush through it because later we have another formula to justify. For endothermic, energy absorbed from the surrounding. And so right now you have lesser way of arranging the energy and entropy decreases. That's it. Nonsense. Skip this part. Just have to write this down. We have another formula to explain on this later on. Okay. Alright guys, next let's look at total entropy change. Alright guys, looking at the total entropy change. So the symbol for a total entropy change, right, is a delta S naught, yeah. Okay, so guys, how do you calculate your total entropy change? Delta S naught total is gonna be delta S naught system plus a delta S naught surrounding. And I need to discuss with you guys your exam schedule already later. Delta S total plus delta S, delta S total equals to system plus surrounding. We said after how many years of teaching you guys? 1 year plus. A delta S total, right? What do we use it for? We use it to predict feasibility. So guys, if your delta S total is a positive value, the reaction is feasible, which means that the reaction is spontaneous. Understand? But guys, if your delta S total is a negative value, the reaction is not feasible, which means it's not spontaneous. Understand? Okay, so which means it will not occur when your delta S total is a negative value. Okay. Alright guys, I can say that right, when your delta S total is greater than 0, reaction is feasible.
Oh, excellent.
Oh, excellent. If it's less than 0, the reaction is not feasible.
Very angry.
Guys, if it's equals to 0, it's at equilibrium.
You're not sweating.
Alright guys, to calculate the delta H of a system, okay guys, I want you guys to write it down. To calculate your delta S system, yeah, I'm talking about the system, it's gonna be delta S product minus of a delta S reactant. Chantele not here. Hao Jie is here. Mingyun is here. Mingyun is here. Wei Men is here. Kwan Lang is here. 谁在 Kwan Lang? Darker color. Why you racist? You like it black?
You like roast?
Roast beef. Nah, darker.
Would be like they ask, is it bubblegum pink or roast? You know what that means?
No. What's a roast beef? Nice. Chun Wei not here, right? I don't see Chun Wei today. Okay, guys, now I want you guys to calculate the delta S system. Go. Please calculate the delta S system for me. Go use your total product minus total reactant. I don't see Shannon and Malcolm. That two fella.
That's a good on your date probably.
Yeah, most probably dating.
I don't think they're dating.
Alright, guys, what is my delta S system? Simon, give me a second, yeah. Let me add you in. Okay, so guys, your value is your reactant, your product is 2 times your CaO 39.7 minus of 2 Ca plus 205, right?
I think this one's chicken.
Done. This chapter is very easy. It's just normal calculation stuff, guys. Do it now.
That's W, but it's a long word. Yeah. Like, man, I went down, I went back up. Why lah? This is no lah, mula. This off one that like this.
Alright, guys, next. Let's look at, they ask you to discuss the validity of the value. So, guys, can anyone tell me why the value is negative? Why? Why the entropy change of a system is negative? No, it's not really. Because you see, from gas to solid, can see that? Gas to solid, there's a decrease in entropy, right? So I can say that it's definitely valid. Why? Because again, I can say that the reactant is in gaseous state, correct? But the product is solid, right? So definitely there is a decrease in your entropy. What else, guys? How many mole in the reactant? 3 mole in the reactant, 2 mole in product, correct? So I can also mention that your reactant is 3 moles, 2 moles product, right? Which means there's also a decrease in what? Entropy, right? Correct. I'm gonna skip all this question. Look at questions, page 7. All right, guys, next we have done calculating the delta S system. Now I want you guys to calculate the delta S surrounding here. So guys, to calculate your delta S surrounding, we can use this formula, negative delta H reaction over temperature. All right, guys, if you look at your value, your delta H reaction, it's always given in kilojoule per mole. This is always given or found in joule per mole per Kelvin. So please go and multiply it by 1,000 to convert to joule for your delta H. Understand? Okay, because your delta H is kilojoule, your delta S surrounding is in joules. So please multiply 1,000. Go. Okay, guys, now I want you guys to calculate delta S total. Okay, I want you guys to calculate your delta S surrounding first. Please tell me what is my delta S surrounding. Go and calculate my delta S surrounding for me. Then calculate my delta S total for me. Now, do it, please. She humbled me. She humbled me. Oops. Oops. All right. Let's look at your delta S surrounding is negative delta H times 1,000 divided by T. Remember, guys, please change it by multiplying 1,000. Reason being, this is in kilojoule, right? So negative maintain. Guys, what is 20 degree in Kelvin? 273 plus 20, right? Answer, please. So it should be positive 4335.2 joule per mole per Kelvin. Is that right?
Yeah, not that. Like, don't see your wife.
What to do, man? She's my sugar mommy. She's my sugar mommy. My sugar mommy needs to continue working.
How she works in Singapore?
So what is my delta S total?
Like Singapore, not.
Maybe. So it's delta S system plus delta S surrounding, right? When you guys start working, so you feel it wanna. You guys now. So guys, what is my system? Negative 208.4. and my surrounding is 4335.2, right? Final answer 4126.8, right? Guys, check your answer, please. You're supposed to do it and compare your answer to mine. And please tell me, what is my conclusion, guys? Is it feasible or not feasible? When your delta S total is positive, it is feasible. So the reaction is feasible at 20 degrees. Understand? Thank you so much. Alright guys, skip your example, skip the exercise. We're gonna do it soon. Page 10. We are almost done, huh? Almost done. Then we're gonna do electrochem later. Okay. You don't have a girl? Get in what? Alright guys, now let's look at your entropy in equilibrium reaction. Alright guys, you see right? Okay, when the reaction goes forward, okay, this is your forward reaction. Okay, so guys, equilibrium, right? Do you see that the gradient or the tangent gradient, your delta S, yeah, your change in entropy, right, is 0 because it's the tangent, right? Am I right? So again, when the change in entropy is 0, okay, so I can say that that is when an equilibrium is achieved, okay? And for example, we have N2O4 turn into 2NO2. At some point in the reaction stops completely. So when the reaction stops, it's when you have your rate of forward reaction equals to rate of backward reaction. This is also nonsense. You don't have to highlight any of it. So at equilibrium, total entropy change of the forward equals to the total entropy change in the backward. Delta S is 0. That's it. Okay, so what you need to know is equilibrium, delta S 0. Done. Next. Alright guys, next. Gibbs free energy. Alright, kid. Okay, looking at the last part, we have Gibbs free energy. So Gibbs free energy, right, measure the spontaneity of a reaction. Okay, and the energy available. Oh, you guys are still doing this trick one. The change of Gibbs free energy is delta G, the symbol. So guys, Gibbs free energy formula, you have to remember this. This is the most important one. Delta G equals to delta H minus T delta S of a system. Alright guys, next. Your delta G, right, it's always in kilojoule per mole. Your delta S is always in joule per mole per Kelvin. Okay, so please take this value, divide by 1,000 to change it to kilojoule. Understand? Okay, so all your delta S value that you are looking at, remember to change it to kilojoule or else.
What the flip?
Let's go what? Where?
That. I don't remember window shopping.
To make comparison of delta, okay, Gibbs free energy, remember your pressure is 10 to the power 5, temperature is 298, and unit is always in kilojoule per mole. Alright guys, next. Your standard Gibbs free energy of formation, unit is kilojoule per mole. Delta G formation is equals to a delta G product minus of a delta G reactant. Gibbs free energy. Okay, again, your delta G, right, is just opposite of your delta S. So when delta G is less than 0, the reaction will occur. So the reaction is spontaneous. If it's less than 0, and greater than 0 is not spontaneous. Okay. Stop for what?
Same. I want to go drink water.
Can guys do the example? Go and fill the water. Guys, what's your answer? So, kid, get me the delta S system first. After you get your delta S system, second, you can get your delta G already. Guys, I'm uploading next chapter, which is electrochem. Guys, we are doing electrochem next. Electrochem is next. Please download the file. Alright, next, delta S system. What's my delta S system? It's gonna be CO2, which is 213.6 plus ZNO43.6 minus of ZnCO3 83.4, right? 117.73.8. Alright, guys, next. Delta G.
It's not that good. What?
Delta H minus T delta S, right? What's my delta H value? Is given as 71 minus of temperature is 298. Guys, don't forget your delta S has to be divided by 1,000, yeah? Please, your value of delta G is plus 19.21. Is that right? So guys, once you get your delta G value, please tell me, is this reaction feasible or not? Spontaneous or not? Huh? No lah, delta G positive is not spontaneous. Remember that it's opposite of your delta S. So if it's greater than 0, it's not spontaneous at 25 degree, right? Alright guys, next. Let's look at delta G with temperature change. Alright guys, okay. You see, right? Delta G equals to delta H reaction minus T delta S. I'm going to call this as a first term and I'm going to call this as a second term. Okay, so I know that, right, generally, if it's negative, it's feasible. If it's spontaneous. Correct. If it's greater than 0, not spontaneous, right? Let's look at your delta H equals to exothermic. So guys, for the first reaction, I do know that my delta H here is negative, yeah? Correct, which is a negative value here, correct? So guys, if your system is positive, okay guys, again, this is the tough part. I'm going to put some stars here. This is the tough part. You have to use your maths skill in it. So guys, delta G is delta H, which is a negative term, correct? Minus a temperature with a positive term, correct? So guys, you see, negative, positive is going to be negative minus temperature, right? Correct, because a positive term combined with a negative is going to be negative, right? So guys, do you see that if you have this equation, right? For example, it's a negative 100 minus 200 times 1000. Okay, so the value of delta G is negative all the way. Am I right? So my delta G, right, is negative all the way. Understand? No matter what temperature it is, right? Okay, be it very low or be it very high, the reaction is always feasible. Okay, so the reaction is always spontaneous at any temperature. Correct. Ayun, Kelvin. And alright, guys, nice. If your system is a negative value now, let's go. Guys, you see, right? Your delta G is gonna be a negative first term, correct? Minus of a temperature and a negative second term. Correct. So, guys, a negative is gonna be a positive, right? So, guys, it's gonna be a negative first term plus a temperature. Am I right? So, guys, under what circumstances your delta G is feasible? Do you want your value to be high or do you want the value to be low? Do you want your T to be high or T to be low? I definitely need my T to be low. Because if T is high, okay, this value is going to be a positive value now, and this is not going to be spontaneous. Clear? For example, let's say this is 100. This value is definitely going to be less than 100. Maybe it's just a 10. At least you will still maintain a negative value. Or let's say this value is negative 100. Let's say this value is a 200. Then gone case already. It turns into a positive. It's no longer spontaneous. So I can say that, right? My delta G is only spontaneous when temperature is low or high. Please tell me now. Okay, when the temperature is low or high.
Everything thermal.
Term, second term, first term. Okay, so delta G is only spontaneous when the temperature is lower. Understand? Okay, next. Delta H equals to endothermic. Guys, if delta H equals to endothermic, your delta H value is positive right now, right? Am I right? So guys, right now, let's do it the second time. Delta G equals to what? A positive first term, right? Because delta H is positive, right? Minus a T, and delta S system is positive, right? Positive the second term. So guys, what is going to be? It's going to be a positive first term. What is minus and plus? It's still a minus, right? All right. All right, guys, now, you see, right? This term, this second term is just a T delta S. So again, guys, now, I want you guys to tell me, your delta G this time is only feasible or only spontaneous under low or high temperature? Under which term has to be big now? The first term or the second term has to be big in order for it to be spontaneous. Spontaneous means this value is negative. In order for you to retain a negative value, your T delta S, yes, the second term has to be very huge. Well done. Under high temperature. Clear? So which means, guys, I can draw a conclusion. If my T delta S is greater than delta H, it's spontaneous. Understand? See which value is bigger. But if your T delta S value is lesser than delta H, it's not spontaneous. Understand? So guys, next. Okay, if your delta S system is negative value, so guys, it's gonna be a positive delta H now, right? Positive first term minus a T negative delta S also. So guys, what is gonna be? Combine it. It's a positive delta H minus is a plus T delta S. Guys, will this value be ever, okay, will this values, right, give you a positive, a negative value? Yeah? Will it be negative? This will never be a negative value, right? Be it you sub 100, 1000, it's still a positive. 0.1, 0.1 is still a positive. So it's a positive value plus a positive value. Your delta G this time is negative, is positive all the way, right? Which means the reaction is not spontaneous at any temperature. Understand? Also the same one. You see, right? 100 plus 100 times a million. Then delta S is that, yeah, negative value. Negative will make it into a positive, right? Understand? For example, let's say this negative 1000. You sub it inside, it's gonna be plus 1000 already. Get it now? Because the negative will cancel to turn into a plus. Get it? Okay, you can randomly sub any value for you to check. So that's the rule. What you guys see? Like the Gibbs energy. Please again that one. Alright, the next question, I'm not doing it. It's okay. So this just formation is product minus reactant. Guys, we are done with chapter 21. Now I want you guys to look at chapter 22. Let's go.
Okay, so that's all for today's topic. So thanks for watching.
Please like and subscribe.